Hi everybody, welcome back. In this video I will introduce solutions and tie it into what we were learning about in the previous videos discussing intermolecular forces. So let's get started. What is a solution? Well, a solution is a homogeneous mixture of two or more substances. And the major component is called the solvent, and the minor component is called the solutes. Or if you have more than one, then solutes. And so let's look at this table here. What I just want to make clear is that many times when we discuss solutions, we will be focusing on liquid solutions, but there are also gaseous solutions and solid solutions as well. And so a gaseous solution is just like the air we breathe, which is mainly composed of oxygen and nitrogen, but it has other gases as well, like carbon dioxide. And then liquid solutions, you can have three types. You can have one where there's a gas as a solute and then the solvent's a liquid. So for example, if you're drinking club soda, that has carbon dioxide and water as the solvent. And then you could have a liquid-liquid solution, and an example of that would be like vodka, where the solute is ethanol and the solvent is water. And you could have a solid-liquid solution, which many of you may have worked with in the first semester general chemistry lab, where you're dissolving an ionic compound in water. A common example in real-world applications is like seawater, where you have salts and water there. And then finally, there are solid solutions. And so, for example, brass, which is a copper and zinc alloy. So if any of you are really into metallurgy, then you're going to be working with solid solutions in your future. So just to summarize, the solute is just the minor component dissolved in the solvent, which is the major component. So it's just all about the amounts. And as you can see here, especially in my course, water generally is the solvent that we use. And so when we refer to something that's called an aqueous solution, I want you to remember that water is the solvent, right? And back in first semester general chemistry, you learned that not everything is soluble in water. Not everything goes into solution in water, and you would have learned the solubility rules. It's really important that you review over these rules and become familiar with them again, because they will be useful for problems in this chapter and future chapters as well. It's always important to understand solubility, and for those of my students who plan to take organic chemistry, you will review over solubility again in the context of organic molecules, but it's just important that we keep practicing that. All right, I want to review over these with you. So compounds that are generally soluble are like the group 1A elements plus the ammonium cation, and there's no exceptions to the rule. So sodium chloride is soluble in water, lithium fluoride is soluble in water, ammonium fluoride is soluble in water. All nitrates, and this is the conjugate base of acetic acid, so that's acetate, they are generally soluble in water as well. So magnesium nitrate, soluble in water. Sodium acetate, soluble in water. So there's no exceptions to the rule. Now, chlorides, bromides, and iodide salts are generally soluble in water, except if they're paired with silver plus 1, the mercury cation, and the lead 2 cation here. Those compounds are generally insoluble when they are paired with these anions. And sulfates are generally soluble except if they're paired with strontium, barium, lead 2, silver, or calcium. And so that's when you have the exception to the rule when it comes to sulfate. So for example, barium sulfate is insoluble in water. Now, compounds that are generally insoluble are hydroxides and sulfides, except when these ions pair with lithium, sodium, and potassium and ammonium, they are soluble. And we remember that from this rule up here, that those cations, when they form salts, are soluble in water. When sulfide pairs with calcium, strontium, and barium, the resulting compound is soluble. And when hydroxide pairs with calcium, strontium, and barium, the resulting compound is slightly soluble. Slightly soluble means that less than 50% goes into solution. All right, carbonate and phosphate, these are generally insoluble except when they pair with those lithium, sodium, potassium, ammonium, then they're soluble. So once again, that's that rule up here that just kind of takes precedence, right? Those are always soluble in water. So make sure you become familiar with your solubility rules. Now for my course, I won't ask you, like, is it soluble or insoluble? Like those specific questions that you probably were asked in first semester general chemistry. But once again, this knowledge will be really helpful for your understanding of solutions in this chapter as we discuss in greater detail together. All right. Now I keep using the word solubility. Let's define it. So solubility is defined as the amount of substance that will dissolve in a given amount of solvent. And it's dependent on intermolecular forces and the energy of mixing. So remember in the last set of lectures, I discussed in great detail intermolecular forces. We learned about dispersion, dipole-dipole, hydrogen bonding, and ion-dipole. And I said in these videos, we are building the foundation that we will use from here on out. And intermolecular force is going to play a critical role in other courses that you will take on your journey towards a STEM major and a STEM career. So we can see directly in this chapter the application of our understanding of intermolecular forces and how it will help us to predict if a certain solute will dissolve in a solvent. In addition, we will be discussing a little bit of thermodynamics, although in future videos I will have a whole set of videos dedicated towards thermodynamics and discussing entropy, enthalpy, and Gibbs free energy. But it'll be nice to introduce the concept of entropy now if you haven't learned it already in a previous course. And like I said, later on we'll discuss it again in great detail. All right, so when we're talking about solubility, things that mix, things that go into solution, we now know it's dependent on intermolecular forces and this energy of mixing, which I'll discuss in a little bit. Now, an example that you may think about, everyday example, it's like grease. Now, if I'm working on my car and I get grease on, on the garage or on the floor, and I want to clean it up, well, I'm not going to use water to clean it up, right? Because grease is pretty nonpolar. It's what we would say, it's kind of fatty, right? It's very nonpolar. And it is insoluble in water. So therefore, I'd want to find a nonpolar solvent to help clean up my grease. And so a very common one would be hexane. And remember when we studied an introduction to organic chemistry, we learned that hexane is just 6 carbons long, just an alkane. And those carbons and hydrogens are nonpolar covalent bonds. So this molecule overall is nonpolar and would be a great solvent to clean up the grease. And so by the end of this video, we will begin applying that knowledge of intermolecular forces to determine if something is soluble or not. So we'll have a lot of practice problems at the end. All right. Now, just want to come back to this concept of mixing and the energy of mixing. Nature has a tendency towards mixing. Things want to go into solution. But why? Like, why is that? And always when you're, as scientists and engineers, you should be acting like my toddlers and asking that question, why, all the time, right? That's what makes a great scientist. And the reason why nature has a tendency towards mixing is due to entropy. So, this comes to the second law of thermodynamics, which states that for any spontaneous process, the entropy of the universe increases. Now, entropy is another way to say disorder or chaos. And the way we represent that, when we talk about entropy, we use the capital letter S. So the change in the entropy of the universe, which I'll abbreviate uni, is greater than 0. That is the second law of thermodynamics. So that states that for any spontaneous process, the entropy of the universe increases. So for spontaneous, and like I said, we'll talk more about spontaneity later on in future lecture videos. And this is all to do with the universe. We're going to later on talk about the entropy of the system and surroundings, but it's the entropy of the universe that must be greater than 0 for a spontaneous process or a reaction. And I always like to give the example of living with 2 toddlers. So at this point in time of my life, I have a 4-year-old and now I have a 2-year-old. And every single morning, the house is all picked up and cleaned from the night before. But the second my kids wake up, they want to play with all their toys. My 2-year-old son takes the buckets out and starts to dump them everywhere. And I've learned to be okay with it. It's taken me a while. But I keep reminding myself that my kids are just proving that the second law of thermodynamics is real, that everything goes towards chaos and disorder. And if you don't have the luxury of living with 2 toddlers, then just imagine the laundry, right? You clean your laundry, you fold it, you put it away, or you hang it up, and it's nice and organized. But a week later, all that dirty laundry is accumulating. Way more disorder, way more chaos than before, right? It's just the natural tendency of life. So let me give you another, a more scientific example. Let's think about 2 noble gases. So I have a box, and the box has a compartment, and I'm isolating 2 noble gases. I'm going to use different color pens here. So I have neon in blue and argon in red. Now let's say I remove that board in the center so that we can observe what happens to these gases. And what happens is that they actually mix with one another. But why is that? Because, when you studied gases and the ideal gas law in first semester general chemistry, you acted as if they never even touched one another, that they did not interact. You assume the ideal gas has no intermolecular forces, no interaction whatsoever. And they don't really react with one another, right? You don't build molecules with them. They're happy. They have their own state of utopia because they already have an octet in their outer valence. And so they don't make molecules, so there's no lowering of potential energy. It's not like when oxygen, which needs 2 more electrons to achieve an octet, partners up with 2 hydrogens, which is willing to share their 2 electrons. And so to make water, which is very stable and low and much lower in potential energy than the individual atoms themselves, right? That doesn't happen here for noble gases. But what's happening, what's driving the mixing of these noble gases, it's not intermolecular forces, it's not lowering of potential energy, it's the kinetic energy. So the kinetic energy is dispersed over greater volume. And basically, that just means that there's greater entropy. Once again, you can think of my son, my 2-year-old son, who likes to throw his toys everywhere on the ground when he wakes up first thing in the morning just so he can play with them. He gets great joy out of the entropy that takes place. So that's what's happening with these noble gas atoms, is that they're spreading out as far as possible and in the sense mixing with one another just because there's greater entropy or greater kinetic energy over the greater volume of that space. All right. Now, the purpose of our conversation here is less to focus on gases, but more to focus on liquids and solids. And remember that liquids and solids are condensed states. From the previous lectures when we discussed intermolecular forces, liquids and solids are close together. And so there's definitely interaction happening. And I just want to do a little bit of review over here. I'm a big believer in kind of reviewing, making sure we feel solid in our foundation of our knowledge. And so in this case here, remembering our intermolecular forces. Remember, there are 4 types that we investigated together. We looked at dispersion forces, which was the dominant force in nonpolar molecules like heptane or pentane, or for example, like those noble gases, neon and argon. Then we moved up to dipole-dipole, which are higher in strength than dispersion forces. These occur in molecules that are polar, like acetone or chloroform, but not in molecules that exhibit hydrogen bonding. Hydrogen bonding is like a super dipole-dipole force, right? It's stronger than their typical dipole-dipole force because the permanent dipole within those molecules is actually much greater. And so examples like ethanol and water exhibit hydrogen bonding. Remember, hydrogen bonding is where hydrogen has to be bonded to an oxygen, nitrogen, or fluorine within the molecule for this to occur. And then finally, the strongest intermolecular force that we studied together were ion dipole forces. And that's when we throw in an ionic compound and it, like, as always is shown, is usually water is the solvent here because we're working mainly with aqueous solutions, but it can be any polar molecule that will interact with the cation and the anion of that salt. And that's what we're going to discuss in more detail in this chapter here. Before my previous lecture videos, I had told you, like, we'll talk about this a little bit more later. And so now we're here. All right, so when we think about a solution forming, I want you to envision this figure here. And I know this figure might seem really simple to you. It's just a bunch of blue spheres and red spheres, but there's a lot lot to think about here, and I think it's actually a great visual. So let's first identify what we're even looking at here. We have a beaker, and one of my favorite phrases you will learn throughout watching my lectures is WHIM, which stands for what's in my beaker. And so you'll always hear me say that, whim, what's in my beaker? Because I'm a big believer in like understanding like what's happening in reality. If you were to go in the lab and to make the solution, what is actually happening in your beaker, even if you can't physically see it, right? And so in this case here, you see that the blue spheres are represented by the solvent, and there's more of them, and that should make sense. Solvent should be in greater amounts, and that the red spheres are the solutes, right? So we don't even care what they are. We're just talking about interactions here in mixing. And so ideally, you want the solvent and the solute to like each other for mixing to occur. So this solvent-solute interactions is when mixing happens, right? So that means they're interacting with one another. But in order for mixing to happen, you have to overcome the solvent-solvent interactions. Remember, the solvent loves itself, right? I mean, clearly it's the same, it's just a bunch of the same, like water molecules, for example. Water molecules love interacting with one another. And so you have to overcome that. You have to split those two apart. In addition, you also have to overcome the solute-solute interactions. And so let me repeat that. For mixing to occur, we really need to overcome the solvent-solvent interactions and the solute-solute interactions. There needs to be a greater attraction between the solvent and solute for this to happen. And this is summarized in this table here. So for a solution to form, the solvent-solute interactions must be greater than the solvent-solvent and solute-solute interactions. Now, there may be a case where they're approximately equal to one another. And here it says the solution generally forms. It generally forms because, like on the previous page, when I talked about neon and argon, those gases and why they mixed, even though they didn't have intermolecular forces, it's because entropy drives the mixing forward. And so this is, once again, it's not only the intermolecular forces, but entropy can also help push a reaction or push a solution to mix with the solute and solvent. And if you do have solvent and solute interactions that are just less than the solvent-solvent and solute-solute, the solution's probably not going to form. It really depends on the difference in magnitude of the solvent-solute interactions versus the solvent-solvent and solute-solute interactions. We do have entropy helping us, right? That the universe wants to go towards more chaos, and so that's the reason why mixing is favored. But it will be dependent on if the disparity between these two properties, right? So for liquids and solids, we need, as we've said before, and I just want to reiterate, we need to take into account intermolecular forces. Now, before we dive into that and picking the best solvent to dissolve a solute, I just want to say that let's say you're making a solution that's a liquid-liquid solution. If two liquids are soluble within one another, they're said to be miscible. And I mentioned this in a previous lecture video before, but I just want to say it again. If you hear the word miscible, that's usually referring to two liquids mixing with one another. Now, if you have two liquids that don't mix with one another, in the example in that previous video, I think I used water and pentane. They don't like each other, right? Polar, nonpolar. So we would call that immiscible. Okay, so immiscible means that it's not soluble. They do not mix. Okay, so let's look at this table here. We have some common polar solvents and common nonpolar solvents. So some common polar solvents we use in the laboratory are water, acetone, methanol, and ethanol. Let me draw acetone for you real quick. It's a dimethyl ketone, like so. And then some common nonpolar solvents. You heard me say hexane already. Diethyl ether, toluene, and carbon tetrachloride. So we talked about toluene. That was a common name of an aromatic hydrocarbon that we've used before when we learned about organic chemistry. Looks like methylbenzene. And diethyl ether looks kind of like a bat. So it's oxygen and then two ethyl groups on each side of it. And the rule of thumb we always use is like dissolves like. Something I did want to point out here that I thought was interesting, glad it was included in this figure, is that diethyl ether does have a small dipole moment. You know, a lot of times when students first learn about polarity, they either think it's polar or nonpolar. It's black or white. But that's not the case. It's a continuum. Some molecules are more polar than others or more nonpolar than others. And so because diethyl ether has this intermediate polarity, it's actually a great solvent for a lot of chemical reactions. When I did research as an undergraduate, diethyl ether was like the solvent of choice when I was running a bunch of Grignard reactions. And it didn't really matter what reactants I kind of started with. It just helped everything go into solution, which was great. And so when you're thinking about the best solvent, if you're designing an experiment in the laboratory, generally speaking, you want everything to go into solutions. That's why it's really important for us to understand solubility. So we want things to go into solution. We want them to be soluble. And so you may have a bunch of choices to choose from. You know, it's not, typically there's more than one answer, right, in terms of which solvent. And so you have to think about other reasons why you choose the solvent you do. Maybe it's because it evaporates easier. So for example, I used methylene chloride quite often in research because it has a low boiling point and I could evaporate it off my reaction at the end. Maybe it's because it's cheap, a cheaper solvent. It's like there's all sorts of considerations. Maybe it's safer. Methylene chloride's a known carcinogen. Maybe it's not the best solvent to use all the time, right? So just some things to kind of consider. So let's practice this. So in this portion of this video, I'm focusing mainly on intermolecular forces. I did introduce entropy to you, and we'll discuss that a little bit more later. But intermolecular forces are going to give you a good idea if something will be soluble or insoluble. So, using the table above, let's pick an appropriate solvent to dissolve each substance. We're going to state the kind of intermolecular force that would occur between solvent and solute. And remember that more than one solvent may work. And I highly suggest, now that you all have a good understanding of intermolecular forces, to pause the video at this moment and try to do these on your own first, and then check your work with me when you come back. And so you're going to look at isopropanol, and then we have more on the next page: sodium chloride, vegetable oil, sodium nitrate. We have an organic molecule here, this alkene. And then ethylene glycol at the bottom there, and part F, okay? Let's go ahead and work on it, and then come back when you're ready. All right, so let's check your work. So isopropanol, what is its main intermolecular force, or its dominant intermolecular force? Yes, hydrogen bonding, good. So definitely hydrogen bonding. Yes, it does experience dipole-dipole and dispersion, but the strongest is hydrogen bonding. And so what solvent did you choose? Yeah, so some of you may have written down water, which is great. When you purchase isopropanol at the store, it's not 100%. Usually it's about 70% isopropanol and 30% water. Methanol also has hydrogen bonding intermolecular forces and some carbons in it, so it might be a great solvent to dissolve isopropanol and then ethanol as well. Fantastic. So you can have more than one, and that's totally okay. Sodium chloride, we recognize it's an ionic compound, so its strongest intermolecular force would be what? Ion dipole, right? And so therefore, what solvent did you choose? I imagine many of you chose water, right? And I wouldn't blame you. That's what I would have chosen too. Right? But remember that you could have used any other polar solvent, maybe like methanol as well, or ethanol too. And if some of you are also suggesting acetone, once again, that also could work as well. Acetone is a little less polar than methanol, ethanol, and water. It has dipole-dipole intermolecular forces, so that's why I'm leaning towards these really polar molecules here. But acetone actually is used as a cleaning solvent in an organic chemistry lab, and there are times where we work with salts. Acetone usually does a pretty good job. But usually in the end, once I acetone everything, I do use soap and water. That always ends up making sure everything is super clean and then a final acetone rinse. But yeah. All right, vegetable oil. What's the most dominant intermolecular force in vegetable oil, or just the major one? Typically, it's actually dispersion, because vegetable oil has a lot those long hydrocarbon tails. Like, I know it has some ester groups in it, maybe even some carboxylic acid groups in it, the little polar head groups, if you've learned that in biology classes. However, having those long hydrocarbon tails essentially dilutes the polarity, right? If you look at the molecule overall. And so really vegetable oil is very nonpolar, and so therefore dispersion would be the dominant intermolecular force. And therefore, what solvent would you have chosen? Good. So hexane would be a great one. Fantastic. Diethyl ether, excellent. And toluene. Just based on the list that's provided. Understand that there's plenty of more solvents out there. All right, sodium nitrate. It's an ionic compound, so we're looking at what type of intermolecular forces? Ion dipole, good. And therefore, just like sodium chloride, you probably wrote down water, methanol, ethanol as some potential options, but mainly water, basically because we're working in a general chemistry course and we're working with aqueous solutions. All right, part E, we have this alkene here, and its dominant intermolecular force is dispersion because we have a bunch of carbons and hydrogens, which are nonpolar covalent. Although having that double bond and those pi electrons can introduce a little bit of polarity, but overall it's pretty nonpolar. And so therefore we would look at those nonpolar solvents like hexane, diethyl ether, and toluene to help dissolve this particular alkene. And then finally, ethylene glycol. What is its dominant intermolecular force? Hydrogen bonding, very good. And so therefore the solvents that we would typically use, water for sure, methanol and ethanol. And like I said, not to say that acetone wouldn't work. It would definitely work here, but I'm just choosing solvents that participate in this same intermolecular forces that our solute ethylene glycol does. All right, I hope that was good practice for you all. And thank you for watching, and see you next time.